بسم الله الرحمن الرحيم. الانترودكشن and the force. اليونت بتاعت الفورس هي نيوتن. نيوتن which tries to change the state of subject, whether it's moving or not moving. The unit of it, as we said before, is Newton. Newton gives a mass of 1 kilogram and acceleration of 1 meter per second. Acceleration yields a velocity over time. The force of gravity equals 9.81 meter per second on any object. So that, in other words, if we can try to correlate a kilogram to the Newton, we'll find that 1 Newton, or I'm sorry, 1 kilogram will equal 9.81 Newton. So we had transferred the Newton as a force to a kilogram weight. The end result is 1 Newton equals 102 gram, a figure that we must memorize. El Pascal and bar. El Pascal, it's the Systemic International unit expressing pressure. As we said before, or we'll tell later on, that pressure equals a force on the unit area. If we want to express force by Newton, we can express it as weight, which will be represented by 102 over the surface area, which is square meter. So whenever I apply such an equation, we find the pressure will be very small. So that this why we use kilopascal instead. One bar, which is the atmospheric pressure, equals 100 kilopascal at sea level. The interrelation between pressure and force, we can see that pressure equals or yields force over the surface area. Clinic application, the first clinic application, we can have 2 syringes, as we can see. If we apply force of the figure of 25 Newton over both of them at the same time, definitely the small one will yield a much more pressure, as we can see from the figure. Why? Of course, because we are dividing a force over the surface area, which is definitely much bigger in the small syringe. Doubling the diameter of any syringe will yield a مساحة of 4 times of the diameter. You see, we have 2 syringes, as we said before. One of them is 2 millimeters and the other is 20 millimeters. So regarding the smaller one, we can divide, as we see, the 25 over 5 times 10 to the power of -5. We can see not to forget that the smaller syringe has a figure of more, which is 5, and the bigger has a figure of 4 times. But this times that this one is 10 to the force of -5, and the other has a 4 times 10 to the -4. Yani one of them is bigger and the minus is less. So if we divide both of them, we will find that the smaller one will lead around 500 kilopascal, whether the other one will yield only 100 kilopascal. Systolic blood pressure equals, as we know, around 120 millimeter mercury. If we divide it by 7.5, we will get by kilopascal is around 16. So definitely 16 is much less than the pressure yield from both syringes. This will be dangerous whenever we apply what we call local intravenous anesthesia, because the local anesthetic may escape under the cuff. This is why whenever I use such a technique, it's better to put the cannula away from the cuff and inject slowly, so that we yield a pressure that will not exceed the pressure under the cuff. Of course, this must be applied of course on syringe pumps and infusion pumps. We must be assured that the cannula is strictly in place, otherwise the fluids can rupture the vein and cause problems. Another clinical application is what we call the bed sore. Suppose we have a patient is lying on the bed, and we have an area of 10 times 10 centimeters, and we have a weight of 20 kilogram. Of course, the 20 kilogram, we can, of course, shift it to a Newton, as we said before, that there is a correlation between Newton and gram weight, so that we can see that 20 will give around 96 Newton. So that when we divide this force over the surface area, will yield around 19.6 kilopascal, which is much more than the 16 or 16 of the arterial blood pressure. This will cause, of course, ischemia. This is the second application of what we know about the correlation between force and pressure. The third one is, as we see, the expiratory valve, and we can see that there is a diaphragm acting from above with a spring, and of course the expiration of the patient acting from below. This will cause the diaphragm to move outwards or upwards or downwards. Of course, the resistance is very minimal, up to that around maybe 50 Pascal can open the valve easily, not causing exhaustion to the patient. So suppose I want to control the patient's ventilation, I screw the valve tightly so that I can compress the bag and induce a controlled ventilation. This is the third application of the correlation between both. The fourth one, which is very important, is what we call the regulators of the reducing valves. As we can see from the first from the figure downwards, we have two types. Of course, we have the first stage and we have the second stage. You can see from the first stage that we have a diaphragm acting also from above by a spring and downwards by a rod. The rod has a bulb at the end of it. It is moving through an opening. It's not well shown in here in this figure, but you can imagine that this rod is being moving upwards, downwards through this opening. We have a low pressure figure on the left and right one. Suppose the oxygen pressure is increased. Definitely the force acting by the spring above or will be more than what is acting below, so that the diaphragm will descend. As long as it descends, the bar that it is attached to it will descend also, opening more, or displacing the bulb of this rod from the opening, making more oxygen to go to the other side, trying to increase the pressure. So this upwards and downwards movements of the diaphragm will try to control the pressure whenever the pressure is decreased. This is the first stage reducing valve. The second stage reducing valve, as we can see from the figure, it is a demand valve. It does not work unless the patient creates a negative pressure, as the firemen workers and the pilots upwards in their planes. And of course, in anesthesia, we use this second stage in what we call the Intenox valve. As we can see from the figure, we have the first stage reducing valve. Attached to it a second compartment. This second compartment, we have a big, large diaphragm. As you can see, this diaphragm is attached to some sort of a bulb acting on an opening also. So this opening is not being opened unless the patient creates a negative pressure. So that so that when the patient creates negative pressure, this system opens, facilitating the passage of oxygen or whatever the interlocks to the patient, so that it does not work unless the patient creates negative pressure. And this is the difference between the first and the second stage. Controlling the second stage, there is a control over the valve, which controls the spillage of oxygen or interlocks gas mixture. We have what we call absolute pressure and gauge pressure. Before I forget, the last item we can mention the application of the correlation between pressure and force, as we see from the figure. This is a safety valve in the old anesthetic apparatus. It utilizes the first stage reducing valve. As you can see, whenever the oxygen is being decreased, the pressure, the diaphragm will descend, and the bulb will descend, making more oxygen going to the other side by increasing the opening. This will create a whistle. This whistling will remind us that something is wrong with the oxygen pressure. Going back to the absolute and the gauge pressure. gauge اللي هو العداد اللي موجود على العداد. You see, so whenever I have a full oxygen tank full, the gauge reads around 137 or 137 bar. This is the full reading pressure of oxygen cylinder. Suppose this, whenever I decrease the amount of oxygen, definitely the pressure will yield a decrease up to whenever the cylinder is empty, it will yield a zero reading. It does not mean that there is no oxygen in the cylinder. No, there is oxygen in the cylinder at 1 atmosphere. Of course, I can remove this amount by sucking to yield really zero pressure. But really, whenever the gauge reaches zero, that means that there is only 1 atmospheric pressure inside the cylinder. Otherwise, if it is less, it can crack. You see? So, in other words, the absolute pressure will equal the gauge pressure plus 1 atmosphere. Actually speaking, that whenever the cylinder is full, it's not 137 kilopascal, instead it's 138 kilopascal. So this is the difference between gauge pressure and absolute pressure. Gravitation forces causing the gravity pressure is from the gravitation force of the molecules of air causing a pressure. Of course, these molecules are changed by density and change in altitudes. You must put in your mind that this weight is changed in such circumstances. There is also pressure in liquids. The liquids also, the gravitation forces act on liquids. We use these liquids in measuring of different items in anesthesia. You see, so the first thing is pressure in liquids. Does the caliber of the tubing system affects the end result of the pressure or not? So we have an example of 2 tubes. The two tubes are filled with water at a height of 10.2 centimeter. Of course, 10.2 centimeters reminds you with the 102 gram weight of Newton. You remember that? So in other words, the height of both tubes will give us a hint about the amount of water present. In other words, one corresponding to water, 10.2 centimeter water will give me 10.2 gram of water. 1 kilogram of water equals 1 liter. So we have 2 tubes. The 2 tubes have a gram weight. Gram weight, yani we have a force. so that we can divide this force over the surface area downwards of the tubing. As we see, we have the 4 centimeter and the 1 centimeter surface area below the tube. We have one as if the force as if we have 4 tubes in it. So the end result to yield the pressure, we are dividing both 10.2 over 1 or over 4 will yield the pressure of 10.2 gram weight centimeter in both tubes. So that we want, in other words, the pressure is equal, though there is difference in the surface area. This is not an orthodox figure. You must refer this figure to the Systemic International System. Centimeter, of course, must be meter. The gram must be Newton. In other words, the end result that we can find the figure of 10.2 gram weight centimeter will yield a 1 kilopascal. So the difference in the caliber of the cylinder will not affect the final pressure. There is another point discussing the height of liquids, is what we call the surface tension. Surface tension is forces between the molecules, or the difference in forces between the molecules in the depths of the liquid and on the surface. We can see from the figure that the molecules inside the liquid are being attracted from all directions. On the other hand, the one on the top are only directed tangentially, as we can see. So we can represent from the figure as if the forces on the surface of the liquid are acting tangentially over a cross line. This forces makes a drop of water become rounded. When you throw some water on its surface, it becomes round because of the surface tension. Tension, as we're going to mention later on, is a force per unit length, not per unit area, as we said in force. So there is a difference between tension and force. What is the importance of the surface tension is the height of the liquid manometers that we use to measure the pressure. The surface tension between the molecules on the top will drag the fluids downward, making an inclination, or as we see in water, it will make a convexity. So this is caused by the surface tension of the molecules on the surface. On the other hand, there are another forces between the molecules of the water and the surface of the tube, the glass tube or whatever. This attraction also affects the height of the manometer. So that we have, as we are using water manometer, we have two forcing affecting the height of the liquid and the shape of it, given a convexity pattern. We must put it in our consideration whenever I want to know the height of the pressure. On the other hand, mercury manometer, because the density of mercury is 13.6 more than water, will cause a convexity. The difference between both of them, that there is not attraction between the mercury, because it's very heavy in comparison to water, and the wall of the tubing. This makes the height of the mercury in a convex way. This is a difference between both, and the importance of knowing that to determine the proper height of the manometer. The slope of manometer, as you can see, بالأواني المستطرقة, if we have a pressure and we have different tubes in different size and different shape, we will find that end result that the height are equal. As long as the pressure is constant, all the height among all the different sizes or shape of tubes are equal. So why do we use inclined tube? As we can see, there is a much difference height in the inclined tube in comparison to the straight one. الطول بيزيد that when the height is, or the difference is observed, I can observe it by my eye. It makes it the reading easier. This is the difference of, this is why we use inclined tubes. This is the difference between mercury and water manometers. We can see that 1 kilopascal, as we said before, elevates the water for 10.2 centimeter. On the other hand, the 1 kilopascal will elevate the mercury 7.5 millimeter. Remember that this one is centimeter and the other one is millimeter. So that whenever I want to shift this 7.5 millimeter to be a centimeter water, I must multiply by 13.6. This is the difference between the both regarding the density. البار أو الكيلوباسكال are high pressures. The importance of them that they are not much affected by gravitation forces or temperature, which will affect the final height of the mercury manometer. All these pressure manometers, we must put in mind that the tube is being opened, exposed to the atmospheric pressure. You see, whenever sometimes we use the mercury manometer, the upper part is being controlled by this so that the mercury will not expel. But there is a tube, an opening this disc which facilitates the passage of air. But this small opening can be obstructed by dirt. This is why you must every now and then try to clean it. The pressure in the manometers is definitely not an absolute, but it's a gauge pressure, because the gravitation pressure is affecting the final pressure, so that the blood pressure, the CVP, are gauge pressure. In other words, the 120 millimeter mercury over 80, it's a gauge pressure. So that if I want to make it an absolute, I must add to it this 760 millimeter mercury. يعني لازم اضيف الضغط الجوي على الضغط بتاع البلاد بريشر عشان يديني الابسوليوت بريشر. البارامتر, as we see, كلمة البارامتر, the device that measures the atmospheric pressure. The difference between it and the other manometers, that the upper part is sealed. It's sealed so that I can measure absolutely the atmospheric pressure. As we can see, 1 bar or 100 kilopascal or 760 millimeter mercury can elevate the mercury manometer to 750 millimeter. This is the atmospheric pressure. Why it's absolute? Because it's sealed from upwards. The vacuum is called Torricelli vacuum. The Torricelli vacuum is around 1 millimeter mercury. You see, the two devices that are being used to measure high pressures are what we call the boarding gauge device. It's based on that we have a large hollow tube, as we can see. This hollow tube is being attached to a gear system. The gear system is attached to a pointer on a scale. What's the importance of the gear system? It exaggerates the response. It makes the response more easily to be observed. So whenever I apply pressure to this tubing, it becomes straightened. So the pointer will move, giving a hint about the oxygen. It is called aneroid because aneros means no spill of water, no water. On the other hand, we have what we call the pillows or the capsule device to measure the pressure. We have two types of it. We have the absolute and the gauge one. As we can see from the figure, that we have a capsule like the accordion, and whenever I applied on the left side pressure, this capsule will be expanded or compressed and will activate a pointer on a scale activated by gear system. On the other hand, on the right one, we have two openings. The two openings are controlled by two pressures. Suppose I want to make a difference reading between both pressures. I apply pressure at each point, and the end result will yield the final pressure. We call this differential pressure transduction. The one, I'm sorry, the one on the left, it's completely absolute because it's not attached to atmosphere, whether the other one on the right is attached to the atmospheric pressure, so that we can call it it is a gauge pressure and not an absolute pressure. On the other hand, there are other units used in the States expressing pressure in the cylinders are pound per inch square. Pound per inch square, as we can see, 1 bar equals 14.5 inch per. I'm sorry. We must multiply 14.5 multiply by a figure, as we know, to give us the real pressure by kilopascal. 14.5 pound per inch square equals 1 bar. I hope that I did my best, and I'll try to improve myself later on. Wassalamu alaikum wa rahmatullah wa barakatuh.